Well, so far we've looked at this idea of work as this transfer of energy, and we developed this equation to describe this with the dot product of the force and the displacement, which we then sort of rolled out into the mathematical expression. Both of them are mathematical expressions, but we introduced the cosine of the angle between the two vectors. So these are two vectors. We get a scalar product from multiplying these two vectors in this way. And then we've also looked at a form of energy that is pretty easy to see, the kinetic energy, where we got this expression, kinetic energy K is 1/2 mv squared. Now what we want to look at is something that's a little bit less intuitive, but with a little bit of exploration we should be able to see. Just using the basic tools that we have already, we should see this idea of what we call gravitational potential energy. So gravitational potential energy. And the thing that makes this gravitational potential energy a little bit less intuitive is it's what we refer to as a latent form of energy that's stored up in a gravitational system. So in a gravitational system. And what we mean by a gravitational system is something where we have two objects interacting via gravity. And a simple example that we can look at is, let's imagine a book falling due to the gravitational pull of the earth, and it falls onto a desk. So this is we'll consider this the book and earth system, gravitational system. So here's our book. We're going to have this drop onto a table that's over here. So this book is going to drop down. Now it's fairly intuitive to see where this energy is when the book hits the table. We get the sound that we hear. We can see the motion happening, but it's a little bit harder to see where this gravitational potential energy must be to create this that end result. So thankfully we have physics to help us out. So let's take a look at what's happening here. The best way to start off was we'll start with a free body diagram, and we'll look at what's happening to the book. So of course, there's the book, and it's going to have the force of gravity acting on it. Of course, we know that this force of gravity is just going to be the mass times that gravitational constant near the Earth, at 9.8 meters per second squared. So this is the force that's acting on the book to make it come down, because of course gravity is what makes it fall. So now we can use the work equation. That's the dot product of the force and the displacement, which then will have the force times the magnitude of the displacement times the cosine of that angle between them. But the good thing is, since the force gravity is acting downward and the displacement is downward, in fact, probably a better thing we'll call it the height that it falls, so the delta H. So since those two are in the same direction, the angle theta is equal to 0. So theta is equal to 0 degrees, and that means the cosine of theta is equal to 1. So because that's equal to 1, this term will disappear. 1 times anything is just anything. So we end up with the force, which is our mg, and our delta H. This is the expression that we typically use. It's a change in energy. And the term that we use typically for potential energy is the letter U. And of course, this is potential energy due to gravity. So this is the expression that we would use for the change in potential energy due to gravity. And interestingly enough, we can actually look at how we got that book elevated, and we would see that if I had a free body diagram again, where now I've got the force of gravity is going to be acting downward, but if I move this up, I apply a force upward to raise it up, we'll use as the simplest sort of motion. We'll work with the upward velocity being constant. And of course, if the upward velocity is constant, then that means that the acceleration is 0. And of course, that would mean that the net force is equal to 0. That means that the applied force is just equal and opposite to the force of gravity, the weight, which is just mg. And so this would be the force. And of course, the work that I would do to raise it up would be applying that force times that delta H. So it's the same thing. It's just that in one case, my direction is up. So I would have this would be, if I use up as being positive, a positive direction. This is positive work that I do. This one here, it's negative work because it's dropping down. So that negative change in gravitational potential then becomes the positive change to the kinetic energy that as it's falling, and then the sound as it hits the desk. And so now that we have the mathematical expression that will help us understand this gravitational potential energy, or the change of gravitational potential energy, how about we look at this book and Earth system and see what kind of numbers would be involved. So we'll sort of set up, let's assume that for the purposes of our discussion, that we drop this from about a foot above the desk. So in the metric system, that would be 30 centimeters. Of course, the g, acceleration due to gravity is 9.8 meters per second squared, or newtons per kilogram if you're looking at it in terms of the gravitational field strength. They're equivalent units. And then the mass of my textbook here, my physics textbook, is 1.2 kilograms. So if we want to look at the change in gravitational potential energy, and of course then the increase in kinetic energy and the bang that ensued, the change in gravitational potential energy is our mg delta H. And of course, I should say that we dropped this, so it went in the negative direction, so that's going to be negative 30 centimeters. So now we can plug in the numbers. So the mass of our textbook is 1.2 kilograms. I'm going to multiply that by this 9.8 meters per second squared. And finally, the 30 centimeters. So this is 30, and it's centimeters. So, of course, centimeters is times 10 to the power of minus 2 meters to get into the standard units. So I'll have kilogram meter squared per second squared, which would be a joule. And this would give us 3.5 joules, is the negative 3.5s. So it lost 3.5 joules of energy in the gravitational system. It must have picked up that 3.5 joules of energy in the kinetic system, and ultimately the sound. So I hope that this helps with your understanding of this latent energy, this gravitational potential energy.